Hello, everyone. My topic is slice optimal partial transport. My name is Yikun Bai, and this paper is collaborated with Göttingen University and the Alan Turing Institute. So in this paper, we provide an efficient algorithm to solve the one-dimensional optimal partial transport problem. And based on that, we propose the so-called slice optimal partial transport distance, or SOPT for short. Finally, we demonstrate two applications of SOPT in the point cloud registration problem and a color adaptation problem. Okay, so what is optimal transport? Suppose you have two measures, the mu and nu, which are normalized to be the probability measure. The optimal transport problem study how to find the most efficient way to move all the math from mu into nu. OT have many applications in statistics and machine learning. However, the classic OT requires the total equal amount of math. So to address this issue, one variant of a framework has been proposed under the name optimal partial transport. So in the new formulation, we allow to destroy mass in the source measure and create mass in the target measure. And the mass destruction and the mass creation have penalty, and the weight is defined by this constant lambda. And in practice, mu and nu are empirical measures. And the OPT problem can be written in this formula. To solve it, you need to solve a high-dimension linear programming problem whose computational cost can be very high. So these three are the existing methods. And in our paper, we focus on the one-dimensional empirical OPT problem. First, we prove the original problem can be further simplified as the following linear alignment problem, where L is the partial increasing bijection. And our main algorithm can be described by these two figures. So the idea is in iteration K, we aim to find the best assignment for x1 to xk to all the y point. The yj star is the best y point for xk. So in this case, we will delete xk because it has a smaller cost. And in this case, we will pair xk to yj star. And in the third case, yj star is already assigned. So there is a conflict, and we will run algorithm 2 to solve the conflict. And algorithm 2 also considers three cases. In this case, we will keep all the previous assignment, and we pair xk to the yj star plus 1. And in this case, we pair xk and yj star, and then we need to redesign the assignment for the previous x point, and we will delete some point. And in this case, we still keep xk and yj star, but we have more free y point, so we will keep all the previous assigned x points. So our algorithm will find the best transportation plan over all the three cases. So theoretically, we prove that our main algorithm can correctly solve the empirical OPT problem. Also, we prove that in the worst case means that in every iteration you have conflict and you have to call the algorithm 2. Then the time complexity is quadratic with respect to the size of the measure. And these two are the numerical result of the running time. The orange line is our method, and the pink line is the linear programming. And you can see our method is about several hundred faster than the linear programming. Okay, so based on this, we propose the so-called slice optimal partial transport. So the idea is we first choose several directions theta. Each direction theta can define one-dimension subspace. We first project mu and nu into the one dimension, and then we use our main algorithm to solve the one-dimensional OPT problem. And finally, we compute the average of all these one-dimensional OPT distance. So we prove that if the ground cost C is a metric, then SOPT will define a metric. Also, you can regard SOPT as a proxy of the original OPT distance in the D-dimension space. Okay, finally, I will introduce the application of SOPT. So first, a problem is called noisy point cloud registration. So in this problem, we are in R3 space. We have two measures, mu and nu. And suppose nu equal to t push forward mu, where t is such a linear mapping. And the question is, Suppose you only have some samples from mu and nu, and the sample have noise corruption. Then how you estimate the mapping T? The idea is first you need to estimate the correspondence between the source point and the target point. And then if you have the correspondence, there is a closed form to compute the optimal parameters. So in our method, we just use SOPT to estimate the correspondence. And this figure shows the running time, and this figure shows the accuracy results. And we find that compared to the classical method, for example, ICP and SPOT, our method is the only one that can correctly recover the mapping T. Okay, so the next application is the color adaptation. In this problem, we have one source image and we have one target image. We want to use the color in the target image to apply them into the source image. So the key point is how you define the correspondence between the source and the target images. So you can use the classical OT, but sometimes the result will look weird. For example, in this one, it will give the dark blue to the sky and the red to the ground. But if you use the OPT-based method, for example, the spot and our method, the result looks much better. Okay, so this is a summary. We propose a new algorithm to solve the one-dimensional OPT problem, and based on that, we propose the slice optimal partial transport distance. And finally, we demonstrate the application of SOPT in these two problems. For future work, we will continue to seek the potential application of SOPT in other machine learning tasks. Okay, so this is the video. Thank you for watching.